Alright, so hi, let's talk subderivations today. Instead of backing everything up to the very beginning and explaining everything from scratch, what I'm going to do is I'm just going to go ahead and run through an example, and I'll talk about some of the rules and the concepts that are involved in this derivation. And hopefully that should leave everybody with a better understanding of the rules that are involved here and what it is that we're doing. So this is a sentential derivation theorem. Meaning that it can be proved from no starting assumptions, right? Notice that there's nothing on the left of the turnstile here, which means that we can just derive this from scratch with no premises or starting assumptions. So you know right away that this proof has to involve subderivations because we're going to have to open one in order to even get the proof started. All right. So when we initially set this up, it's going to look like this. So we can write our goal in down here on the main scope line, but again, we have no assumptions to begin with. So we have to assume something to even move this forward. Now what we're trying to do here is prove a conditional, right? A conditional is a sentence of the form if A then B, and this is the kind of thing that you prove with a subderivation, because the way that you would even prove that this is true, if A then B, is to hypothesize that A is true and then do whatever work you need to do within that subderivation to show that it leads to B. So you open a subderivation with A, do whatever work you need to do in there to get B, then you know A leads to B, you can close this out, and back in your main proof, write if A then B, okay? In this case, this is our A, and this is our B, right? So we're going to start by assuming the antecedent of the conditional. And that's what you do anytime that you have to prove a conditional. Anytime you have to prove a conditional, you start by assuming the antecedent. So here we go. Oh, excuse me. That should be it needs to be in its own subderivation. Okay, and we need to state why we're making this assumption. In other words, what rule we're trying to employ. And that's just kind of a pedagogical device. It's for students to keep you from opening unnecessary subderivations. We want you to know where you're going with the subderivation when you start it. So the rule that we're trying to use here, we're trying to derive a conditional. So what we're trying to do is use conditional introduction. So we're going to write A/conditional I over here. So what is it that we're trying to get in this subderivation? We're trying to show that this assumption is going to lead to this. Okay? So this is our new goal. Excuse me. I'm kind of all over the place today, sorry. This is our goal, right? Not P and not Q, the consequent of the conditional that we're trying to prove. So we're trying to get from here to here. All right, so let's think about how we're going to do this. Let's reason backwards a little bit within this subderivation. This is a conjunction. It's a conjunction of two things, not P and not Q. So it seems like the smart way to get this is to derive not P and to derive not Q, and then whenever we get those, we'll put them together with conjunction introduction, right? And then we'll have what it was that we were trying to get in this subderivation. Well, let's start with not P. Let's think about how we can go about getting not P. It doesn't look like there's any direct way to get it, right? There's no there's nothing that we really have to work with that we can apply non-subderivation rules to. So we have to make another assumption. We have to open another subderivation. And in a case like this, when you don't see any other way to get what you're trying to get, what you need to do is open a subderivation and do what I call assuming the opposite. If what you're trying to get has a negation on it already, assume what's there without the negation. If it didn't have a negation on it, you'd assume it with a negation. In this case, we have a negation. This is a negation already. So we're going to assume it without the negation. And what we're trying to do is get this with a negation on it. Okay? So we're trying to introduce a negation. We're using the negation I rule. Okay, so what are we trying to do here? This is a central concept to proof by derivation. What we're doing is assuming something, and we're going to show that this leads to a contradiction. In other words, it can't be right because it's going to cause a clash here. We're going to wind up with a sentence and an unnegated version of that sentence within the same subderivation. And that's going to show that whatever assumption we made that opened up that subderivation has to be wrong. In other words, we're going to show that this assumption is going to cause trouble somehow or cause problems, and so that assumption has to be false. Okay? So in other words, we're trying to show that P must be false, that not P must be true. That's what we're trying to do in this space here. All right, so how can we go about doing that? Well, look, we know we started this whole thing on the assumption that P or Q cannot be true. But we know if P is true, then P or Q is true by that old disjunction introduction rule that we learned like a couple weeks ago. So by disjunction introduction on line 2, we get P or Q, because if P is true, P or Q is true. Now, I think you can see that P already got us into trouble, the assumption that P already caused a problem, right? We have a contradiction here between lines 1 and 3, but just as a matter of bookkeeping, to show that we have a contradiction in this subderivation, we need to reiterate line 1 down here onto line 4. That's why we have that reiteration rule in the first place. Okay, so we've shown what we wanted to show. We've shown that the assumption of P causes a problem. It causes a clash between P or Q and not P or Q. So P has got to be false, at least on this assumption, on the assumption that not P or Q. P is false. So line 5, we can close this subderivation, come back out to the next subderivation, and we have not P by lines 2 through 4, negation introduction. At this point, it would be a good idea for you to pause the video and see if you can get not Q. Okay, because it's going to look pretty much exactly the same. But we're just going to assume Q for negation introduction. Then we're going to get P or Q by disjunction introduction. No surprises there. Now, just to keep things nice and neat, we're going to reiterate line 1 down here. We've shown that Q also leads to a contradiction, right? So Q must be false by lines 6 through 8. And now we have both not P and not Q. We can put them together. So we've shown that the assumption of not P or Q leads to not P and not Q. So we can come out of this assumption or come out of this subderivation, okay, back out to the main proof. And we can say that not P or Q, then not P and not Q. If not P or Q, then not P and not Q. Okay? So we proved the conditional that we wanted to. So 1 through 10, conditional introduction. And we're all done.